what we're going to talk about today is a single sideband AM. So let me write it down. Single sideband amplitude modulation, or just shorthand SSM or SSB, single sideband amplitude modulation. So far we covered double sideband modulations, double sideband with large carrier and suppressed carrier. And what we've seen, all the double sideband modulation, either a large carrier or suppressed carrier, require 2 times W at the carrier frequency. For the transmission of the signal. Here, W is the baseband bandwidth of the signal itself. It is, we assume that our message signal M of t is band limited so that it extends in the frequency range from 0 up to 2W. So we discovered that if you were to use any one of these double sideband schemes, we end up needing 2 times more spectrum at the carrier frequency than what we needed at the baseband. Also, what we know is that when you do the translation in a frequency domain from the baseband, you end up with pairs of sinusoidals that are redundant, because whatever I have in the lower sideband is the same information that I have in the upper sideband. So intuitively, we should be able to understand that you don't need both of these sidebands. You can just get away with one of them if there is a convenient way to reconstruct the other. Because there is no new information in one sideband relative to the other. They're the same information, just slightly shifted in phase. So let me put that as a note as well. The information in sidebands is redundant. Which means that if I know what's in one sideband, I should be able to reconstruct what's in the other one without any ambiguity. Now, in a lot of cases, that is not a concern, because we have a lot of cases, the prime concern is the cost, right? And it turns out that both double sideband suppressed carrier, but even more so double sideband large carrier, is very simple to modulate and demodulate. But there are a lot of applications where the bandwidth is the prime resource, wireless applications being the best example. And in those kind of applications, we have to do everything in our power to minimize the utilization of the spectrum. And the single sideband modulation is a very good way of doing so. So how does the single sideband work? Well, let's take a look at just the basic idea. And this is just saying, okay, if I were to do it, how would I actually, what math does it need to happen? You will see right away that this initial idea is not very practical, but fortunately we'll be able to kind of go through the math and demonstrate that you can do you can accomplish the same result by processing the signal at the baseband and then translating the resulting signal to the RF frequencies. So what is it that I'm trying to achieve? Well, I have my modulation signal, M of t, and let's say following the same approach I had for double sideband signals, I'm going to use the signal to modulate my carrier. So this will give me a double sideband signal, Z of t. And what I'm going to say now is, let me take that signal and remove one of the sidebands. Let's say I use a high pass filter to remove the lower sideband, but you can use the low pass filter to remove the upper sideband just as well. The math is going to be the same. It's just that for the derivation I need to pick one to demonstrate what is going to happen. And here I'm going to get U single sideband of t. How does the picture of this look in a frequency domain? Well, I'm going to start with my message signal, which we have been drawing like this. Really the only important thing here are these W's. The spectrum of the signal looks however it looks. So this is frequency and this is M of f. So this is the spectrum of my message signal, this guy here. After the spectral translation through this modulation here, I have the frequency of the carrier. I'll be using FC, so let me stick to that notation here. FC, and this is minus FC, F. And here's what happens when you translate the signal. We know that this is here m of m of f plus fc, and there's a 1/2, and this is 1/2 m of f minus fc. All right. So these are the two sidebands, and what we're trying to do with this high-pass filter is essentially remove the lower sideband, and kind of this is the transfer function of the filter. So this is what gets, passed at the output of the filter, and this is what gets eliminated. Now the question is how we're gonna write this whole thing in a frequency domain. Well, we start. Let me just put here in frequency domain. We have that m of t through Fourier transform gives me m of f. That's this portion here. Now u double side of t, which is the same as the signal z of t, is going to be equal to, is going to give me a Fourier transform as 1/2 m of f plus fc plus 1/2 m of f minus fc. So that's the Fourier transform of the double sideband signal. And then now we need essentially the Fourier transform or frequency response rather of this filter that is doing the filtering, this guy here. Because we know that the spectrum of this one is going to be whatever is the Fourier transform of z of f times the transfer times the frequency response of this filter. So we're going to do that in a frequency domain, and then we're going to go back to the time domain and see what actual processing do we need to do on a signal to accomplish the task. So to derive the frequency response of this filter, I'm going to define, so the filter, let me call this h of f. So this high-pass filter, h of f will have a transfer function that is given as follows. It is going to be 1 whenever f is greater or equal than fc, and 0 otherwise. Right? That's what we require, because this is equal to 1, and it is equal to 0 because we're trying to reject the lower sideband of this particular signal. Now I can express this in a more convenient way using a step function. Which is defined as u of x is equal to 1 when x is greater than 0 and 0 otherwise. I can express this filter characteristics as follows. I can say h of f is going to be equal to u minus f minus fc plus u of f minus fc. This guy here is the right-hand side, and this guy here represents the left-hand side. You can see here, whenever f becomes more negative than fc, then this whole thing becomes positive. So this is the step going in this direction, starting from fc, and this is the step going, of course fc is here in the middle. This is the step going in a positive f direction, starting from fc. So now, using all of these definitions, I can see in a frequency domain, that I can write u single sideband of f as essentially this double sideband. So u double sideband of f times this u of f, right? Because filtering in a frequency domain is nothing but the multiplication of the Fourier transform of the signal and the frequency response of the filter. Of course, this is not u of f, but what? H of f. Right. So now, let's go back and put all of these into this equation and see how far we get by manipulating some of these equations. What I'm going to do is I'm going to leave this section here, this figure, so that we have clear understanding of what is going on, because the equations will tend to get a little bit messy as we go through these derivations. So let me do that. So, if from now I can say U single sideband of F is going to be equal to 1/2 M of F minus Fc, that's this part of the spectrum, times U of F minus Fc, which is this section of the filter, this guy here. And then all of that plus 1/2 M of F plus Fc times U of minus F minus Fc. Right? So this is the filtering, on a positive frequencies. This is filtering on a negative frequency side. Now, this can be rewritten as, and this is an important step in the sideband of F. I can see this as being 1/2 M of F times U of F, and then for F equal F minus Fc. You can see that this and this is the same thing, but F is equal to F minus Fc. And then plus 1/2 M of F times U of minus F for F equal F plus Fc. Right. So just formally approaching these equations, we can say that this is the case. Now, why is this important? Because we know what this is. This is a frequency translation, right? And frequency translation is just multiplying by appropriate exponential. We'll do the frequency translation. This is filtering M of F times U of F. This is filtering the upper side, and if you think about what this does, is if this is M of F, the first equation gets this portion, right? So this is coming from the first equation here. And what this says, filter this part and then translate it here, right? What this equation says, filter this part and translate it over here, which is exactly what needs to happen. So this is the second equation, this guy here. Okay? So now, armed with what we've learned so far, we need to look at how we're going to implement this in a time domain. So let's, taking the inverse Fourier transform, taking inverse Fourier transform of this equation here, we end up at U single sideband of T is equal. I can put 1/2 here, which all of these constants up front are not that important. These are just scaling factors that you can bring up or down depending on amplification in the circuit. What is really important is what is happening along the frequency axis. How are you moving all of these spectral components around? So this is multiplication in a frequency domain. What does that translate into time domain? If I have multiplication in frequency domain, this is convolution in a time domain. So this is going to be M of T convolved with an inverse Fourier transform of U of F, and then translated to the MCT, translated in the frequency domain using this kernel here, this exponential. And then here this becomes 1/2 M of T, inverse Fourier transform of u of minus f, and then translate it to pi fc t. Again, translate it in a frequency domain. So now, what is the Fourier inverse Fourier transform of this? From table 2.1 in your book, from table 2.1 in the text, you can easily find out that, let me see, Fourier transform of u of f, inverse Fourier transform of u of f, is going to be 1/2 delta of t plus j over 2 pi t. Oh, sorry, not 2 pi, 2 pi t. And also you can find that the inverse Fourier transform of u of minus f is going to be essentially the same thing, but complex conjugate, right? So it's going to be 1/2 delta of t minus j over 2 pi t. Right, so those are the inverse Fourier transform of these guys. So now I can substitute everything, you know, into this equation and get that u single sideband of t is going to be 1, I can say, let me just write it, m of t, convolved with 1 over 2 delta of t plus j over 2 pi t, and then plus 1/2, again, m of t, convolved with 1/2 delta of t minus j over 2 pi t. So this gives me a recipe what needs to happen in a, oh, and I forgot, I knew I was forgetting something. There's, what is missing here? This exponential, right? E to the j 2 pi fct. And then I have, again, 1/2 m of t convolved with 1/2 delta of t minus j over 2 pi t, and then e to the minus j 2 pi fct. I'll have it. So again, what I understand here is I have to take the m of t, do some processing in baseband, which is this filtering, and then perform the translation to a carrier frequency. So let's spend a little bit more time in understanding what this thing is about. What kind of processing need to happen in a baseband? I haven't really mentioned it, but let me spend a couple of seconds explaining why do we need to do processing in a baseband. Look at this FC can be relatively high in frequency, as you know. For example, if you're doing radio broadcast, then you're translating to hundreds of megahertz. If you're doing, cellular broadcast, it can be several hundreds of megahertz, even a few gigahertz, right? So FC can be very high relative to W, right? This is FC plus W here, and FC minus W, and the same thing on the other side. So getting a step function filter at a very high frequency is close to impossible. So even though this illustrates the idea, this is not a practical way how we can do this. Now, so we need to have a better way of accomplishing the same task. And what we are doing here, we're actually, instead of filtering this at a high frequency, we're going to devise some filters at the baseband so that we do all the pre-processing where it's easier to process the signal, and then in the final step move the signal to the carrier frequency that we desire. So that's the motive why we're trying to bring this to the baseband, because even though the idea is clear here at the carrier frequency, it is not practical. You cannot do this kind of filtering to get this kind of selectivity at a high frequency. So continuing here, I can bring this m of t and do the convolutions. What is the m of t convolved with delta of t? If I take any signal and convolve it with delta pulse, what do I get? I get the same signal back, right? So m of t convolved with delta of t is back my m of t. So I can now say u single sideband of t is going to be, let me put 1/4 here. This is going to be m of t plus j m hat of t. whatever that is. What is the m hat of t? It's the convolution with m of t and this 1 over pi t, right, which is impulse response of some filter. Yet I don't know what that filter is, but at least for right now, I can say there is a filter that has an impulse response 1 over pi t that I need to pre-process, that I need to run this signal through. And this, what comes out of that, I'm going to call it m hat of t. And there is e to the j 2 pi fct upstairs. And then I have downstairs very much the same thing, m of t minus j m hat of t times e to the minus j 2 pi fct. So that's just this same equation rewritten. I haven't done anything really to get here. All I did is just took m of t in convolution with y over pi t, and I called that m hat of t. I still have to explain how do I actually do this convolution and what in the world is this filter that has this kind of frequency response. That still needs to be explained more thoroughly. So I can say here where m of t is obtained as m of t in convolution with delta of t, and this m hat of t is m of t in convolution with this 1 over pi t, whatever that may be. Now, there is these exponentials, which, you have a positive one, you have a negative one. By now, you should have enough experience to say, well, this smells like a cosine and sine. So, sure it is. So let's manipulate this to put it into slightly a better form. I'm going to erase this. I don't think we need it anymore. So now if I group this by these m of t and m hat of t, I can say that single sideband of t becomes 1/2 m of t. Now I grab the positive exponential from the first one, negative exponential from the second one. So I get e to the j 2 pi fct plus e to the minus j 2 pi fct divided by 2. So that's the first guy. And then I can say minus 1/2 m hat of t. And then from the first one I have a positive j 2 pi fct minus e to the minus j 2 pi fct and then j 2. Okay? So now you can see that what is this part here? This is a cosine, and what is this part here? That's a sine. So I can write this as a 1/2 m of t times cosine 2 pi fct, and then minus 1/2 m of t m hat of t times sine 2 pi fct. So all of a sudden it becomes really clear to see what is it that you need to do to get a single sideband modulation. You have to take your original signal and do your double sideband thing, right? Just like double sideband suppressed carrier. You have to take the same signal and filter it somehow and modulate that using the sine now, which is the same as this, but just shifted by pi over 2, and add these two signals, and somehow magically they will cancel the lower sideband at the carrier frequency. You're doing all the processing here at the baseband, but when you translate this, it will actually remove the remove the lower sideband from the spectral content of the signal. So let me just get this as a summary here. So if I want to use single sideband, but if I want to keep the upper part, I'm going to say that this is going to be equal to 1/2 m of t times cosine 2 pi fct minus 1/2 m hat of t times sine of 2 pi fct. If I want to remove the upper sideband and keep the lower sideband, you can go through essentially the same math, but and the only difference is going to be that the sign here between these two functions is going to be plus times sine of 2 pi FCT. So we've learned that we can generate the sideband by doing all the processing at the baseband. The only thing that is left now is to understand what is this filter here. What kind of processing will take my signal m of t and give me this m hat of t. So let's take a little bit closer look into this, this filter with the impulse response 1 over pi t. What kind of processing is that? So, m hat of t is going to be m of t convolved with 1 over pi t. If we expand on this convolution here, this is an integral when tau goes from minus infinity to plus infinity, m of tau 1 over pi t minus tau d tau. So that's the convolution here. I'll comment a little bit later. This is actually one of those linear transforms. It's a known, but so far all we know is that there is some filter that has this impulse response which I need to pass my signal through before I obtain m hat of t. Now so the impulse response of the filter h of t will be 1 over pi t. The frequency response of this filter, h of f, is going to be Fourier transform of h of t. And after some little bit of work there, you obtain that the Fourier transform of this is minus j sine of f. So this is the Fourier, the frequency response of this filter. So how does this look like? Well, if you look at the magnitude of h of f, it looks like this. F, it's this, right? It's 1. Possibly at this point here, it's just it's 0. But the point DC component is really not relevant. No signals we allow them to have DC components. So that's the magnitude response. The phase response of this filter is going to look like this. For a positive f, sine of f is going to be 1. So it's going to be minus j. Minus j, the phase of that is what? Minus 90 degrees, or minus pi over 2. So this is minus pi over 2. For negative f, sine of f is minus 1, and this minus 1 gives me plus j. So this is pi over 2. So this is the magnitude response and the phase response. Now, there are some things that, so I can say here in summary, h of f is going to be equal to minus j for f greater than 0, 0 for f equal to 0, and plus j for f smaller than 0. So that's the frequency response of this filter. It is a little bit, you can see right away that that's not physically realizable because, you cannot have these continuities like this and sharp edges. But it is conceivable that we can design something that looks like this, that approximates this in approximation that's close enough. And fortunately, most of our signals have a certain band here that where they contain no frequencies. If you think about voice, when do the voice, for example, when does the voice start? What is the spectrum of the voice? We can say telephone voice starts about 200-300 hertz. So there is this region from 0 to 200 hertz where really whatever the frequency response of this filter looks like is not very relevant, right? So what you need to have is, if this is the lowest frequency of your signal, that's where this one needs to be approximately 1, and then this is your W, right, where the signal ends. Now, for practical purposes, this one is an all-pass filter, right? It passes all the components of the spectrum, and all it does is the phase manipulation. And if you think about it, what happens if I had a sinusoidal here? Because of the magnitude response being equal to 1, the magnitude of this sinusoidal is going to stay the same, but its phase is going to be delayed by the angle of pi over 2. So if I take a cosine and delay it by pi over 2, what is it actually that I get? Let's just take an example and so that we can understand what is happening. Consider a component in the spectrum of the signal. Let's take a component S of t, which is cosine of 2 pi f0t. And let's say S minus 90 of t as a cosine 2 pi f0t minus pi over 2. Because that's what this filter will do. If I have a component in the spectrum of my signal, it will preserve its magnitude, but it will delay the phase by pi over 2. Through simple trig identities, you know that this is cosine 2 pi f0t times cosine pi over 2 plus sine of 2 pi f0t times sine of pi over 2. Well, what is the cosine of pi over 2?
0.
0. So therefore, what is the sine of pi over 2? It's 1. So this becomes sine of 2 pi f0, of course, t, missing here. So what does this filter do? Now it's very easy to understand. What do I need to do? I need to look at my signal through my Fourier glasses, see that it consists of all of these sinusoidals, take each cosine and turn it into sine. And then I go do that for every one of the signals, and what I get as a result of that is my signal m hat of t. Then I take the m of t, multiply with cosine, m hat of t multiply with the sine, add them together, and this results in the cancellation of one of the sidebands. So this transform here has its name. The transform that takes the spectral components of the signal and delays them in phase by pi over 2 has its name. This thing here is called Hilbert transform. It's an integral transform, very similar, linear transform, very similar to like a Fourier transform or Laplace transform. It has a very interesting properties on its own. But for what we needed here is we have to understand that the Hilbert transform takes every spectral component of your signal and performs its phase delay by pi over 2, turning essentially every cosine into a sine. So finally, I get U single sideband of t. If you remember, that was 1/2 m of t cosine 2 pi f0 t minus 1/2 m hat of t times sine of 2 pi f0 t. If I were to draw this as a block diagram, I should say, I'm going to write Hilbert transform, or a lot of times, actually, let me just do it this way. A lot of times you just write like this. This is Hilbert, or you say e to the minus j pi over 2. Understanding that what you need to do is take every component of the signal and translate it by 90 degrees. You get m hat of t here. Now you take this guy and you multiply that with a, let's say, cosine 2 pi f ct. That's your carrier. Here you get m of t times cosine 2 pi f ct. Down here, you take the same oscillator and you delay it by pi over 2 to get what? To get sine 2 pi fct. You use that to modulate your m hat of t, and then you take these two signals, add them together, and this becomes your U single sideband of t. This is, of course, the upper. If you want to have a lower, then you would have plus on both sides here, adding these two components, right? If you want upper sideband, then you take this one with positive and this one with a negative. There is a scaling factor 1/2, but that's not really relevant, because here you have you still have to amplify and transmit it and so on. Any questions on this? The big thing here is that all of this is done at the baseband, where you can actually do this kind of filtering, right? And then you translate everything using this oscillator. This is a very common architecture. You will see later in your school that this is what we use extensively in all digital communication. We call this component I and we call this Q, and this is a balanced I and Q modulator. So this is very much very common, right? Where you don't use a single cosine, but rather cosine and sine in pair. And a lot of modulators come essentially with this circuitry built in there, where you have a carrier and its quadrature already available on the very chip. Okay, so that's how we modulate. Before we start talking about how you actually get your signal back, I want to point out something that is unique to this modulation when it comes to the world of amplitude modulation. Strictly speaking, we say amplitude modulation is the modulation that modifies only the amplitude, where all the information is in the amplitude of the signal. But if I look at this expression here, I can say U single sideband of t is equal to 1/2 m of t times cosine 2 pi f0t minus 1/2 m hat of t times sine 2 pi f0t. Well, I can use the trig identity to rewrite this as 1/2 m of t squared plus m hat of t squared taken as 1/2 times cosine 2 pi f0t plus arctangent m hat of t divided by m of t. What is it that I use here? I use our famous trig identity that a cosine alpha plus b sine alpha is equal to square root of a squared plus b squared times cosine alpha minus arctangent b over a. That tells us that if I add sines and cosines of the same frequency, the result is always going to be single sine or a cosine with appropriate magnitude and appropriate phase. Now, both m of t and m hat of t are a function of time. And if you look at this waveform, really what jumps out right away is that amplitude is modulated. It's a function of time. But phase is modulated too. So single sideband, even though we say it's an amplitude modulation and we teach it as a part of the modulation, it's actually very complex modulation. It changes both the magnitude and the phase of the signal in a fairly complex way. It's a non-linear, and therefore it is, I would say, in lack of a better term, pretty fragile. You have to handle it with care, because a lot of, if you have non-linearities along the way or whatever impairments, they may offset very fine relationships between phases and magnitudes and become, and then it becomes relatively difficult to reconstruct your signal back. So now let's take a look at how you would demodulate. Of single sideband AM. Single sideband is demodulated coherently, meaning that to be able to demodulate this, you have to have a local carrier with the same, with appropriate frequency and the phase. Now, there are difficulties associated with generating local carriers, and in systems that are practical and are using a single sideband modulation, it is not uncommon to send a signal and the carrier along the way with the signal itself, so that you don't have to generate it locally. You can use the one that you receive to amplify it and use it for demodulation of the signal. I'll talk a little bit about it at the very end when we talk about multiplexing, because the big use where these signals had was in analog telephony, and there's still some of it left in the world where you use a single sideband to transmit a lot of telephone signals over a single transmission line. But going back here to understand how you would demodulate, you would take single sideband signal, and let's for right now try this. I'm going to multiply this by the cosine 2 pi f0t, get my signal here that I call x of t, and then try to do some filtering in a hope that I get back my, let's say, y of t, and we'll see what that y of t is and how I get my signal back. So if I plug this and then take this signal, multiply with the cosine, you get that x of t is going to be u single sideband of t times cosine of 2 pi, and I keep on writing f0, fc, right? I hope I messed it up here as well, right? It needs to be fc. fc, fc, c, I hope, yeah, here as well, right? Everywhere. C, 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 C. C stands for carrier, right? And I think in this course we use C. Okay, here it's okay. So 2 pi fct. So let's substitute what this means. This is 1/2 m of t cosine 2 pi fct minus m hat of t times sine 2 pi fct, and then times cosine of 2 pi fct. Right? That's what's happening there. But right now you know that cosine times cosine gives you 1/2 of 1/2 plus 1/2 of a double, and then this is just a 1/2 of a double. So this becomes 1/2, or I can say 1/4 m of t plus m of t cosine 2 pi times 2 fct minus m hat of t times sine of 2 pi times 2 fct. Okay? So now we see that there are 3 terms here. Let's just look at them a little bit in frequency domain. Where is the spectrum of this signal?
The base.
It's a baseband, so this is from 0 to W. Where is the spectrum of this signal? It is centered around 2fc, so way higher in the frequency domain, right? It is from 2fc plus W to fc minus W, right? That guy. Well, where is the spectrum of this signal here? Same. What if you look at this? What is this? This is a single sideband signal now at the frequency at 2fc, right? So I moved portion of it in double the carrier, and then I move the rest of it at the baseband. Now if I let this low pass filter everything from 0 to W, what is going to be y of t? Y of t is just going to be this part. The rest of it is going to be removed, and as a matter of fact, this filter has a very easy task because the components of this is very, very far away in the frequency domain. So this is a relatively low selective low pass filter. The bandwidth of this filter is going to be motivated by how much of a noise do you want to put in the system. But as far as filtering the double frequency components, it has a very easy task. So this y of t is going to be proportional to m of t itself. So as long as you have a good estimate of the carrier frequency, you can demodulate the single sideband in very much the same way that you used to demodulate double sideband with the suppressed carrier. Okay. Let me see what else is in here. So let's talk about signal multiplexing in frequency domain. The reason, the motive for all of these modulation schemes, one of the biggest motives is to be able to transmit multiple signals through same transmission medium, same transmission line. We said there are two principal reasons why we modulate. One is to adjust the properties of the signal to those of the medium. Medium, you know, which is the physical reality through which the signals travel, can have properties that favor one frequency band over the other. If you're transmitting through the lines, then you want to be, you know, closer to the baseband or to some cutoff frequencies. If you're doing wirelessly, then you want to be much higher in a frequency band, because then you can have reasonable size antennas and other requirements. So one motive why we do modulation is to be able to move our signal around and use whatever frequency band we desire to. But the other one is to be able to share the same frequency band with, between multiple signals. If you have multiple voice transmissions, all the voice transmissions are generated in the baseband. And if you want to use the same line to transmit all of them, you have to stack them up at least in a frequency domain so that they don't interfere with each other. And that's the origin of the simplest multiplexing scheme, which is called frequency division multiplexing. And let me talk a little bit more about frequency division multiplexing, because now we have all of these three modulation schemes. Each one of them give us the flexibility to translate the spectrum from baseband to whatever carrier frequency we desire. The double sideband modulation schemes need two W, single sideband needs a W, but nevertheless, the idea is the same. If I'm able to put it in a frequency domain wherever I want, why can't I stack them up one next to the other and then use the same line to connect the transmitter and the receiver? So let's talk about the basics of FDMA. So, signal multiplexing in frequency domain. So, see, modulation, the property of the modulation that we're going to be using here is the translation property. It translates signal from baseband to carrier frequency. Bandwidth required depends on the modulation scheme that we use. If we use double sideband, either large carrier or suppressed carrier, what do we need? 2W. If we use the single sideband scheme, then we need just a W. Okay? The easiest way to understand what is happening here is through an example. Let's say I have two signals, and they're both baseband signals, let's say from 0 to W. This is M1 of F, and this is the signal M2 of F, minus W. Let's say this is my M1 of F, and just so that to be cute, I'm going to say this is M2 of F so that you visually see that they're different. Let's say I take this one and I use the frequency FC1 to modulate, and use FC2 to modulate this one. And let's say I use double sideband suppressed carrier, just for the sake of example, so that my pictures are easy to draw. Well, what will happen, and this guy here, let's say this is FC1, I will translate the spectrum of the modulated signal. This is FC1 plus W FC1 minus W. This point here is FC minus FC1 plus W, and this is minus FC1 minus W. So this would be M1 of F minus FC1 plus M1 of F plus FC1, and then 1/2, because just to make the math work. So this is where the signal is in a frequency domain after modulation. This guy here is going to reside in a different portion of the spectrum. Let's say this frequency here is what I call FC2. And I have to economize with the board, so let's say this is the upper portion, and then here somewhere, my FC2, I'm going to have a lower portion. This becomes now 1/2 M2 of F minus FC2 plus 1/2 of M2 F plus FC2, right, this signal. And this is centered, this lower point here is FC2 minus W. And as long as these 2 points don't overlap, I have a means of separating. All I have to do is proper filtering. So that gives me if I'm modulating signals of a bandwidth W, that tells me that the separation between these 2 carriers has to be at least 2W plus a little bit more to allow for filtering. So if I now add these together in a frequency domain, you end up with a picture that is somewhat like this, right? Where this is your first signal. Actually, I started being cute and I didn't continue, right? So this doesn't look like a triangle, right? It looks like this to make sure that they are different. So you have stacked them up in a frequency domain. This is frequency, this is a carrier FC2, this is a carrier FC1, and this is now M1 of F when F is FC1 plus M2 of, I should really just write this as sum of modulated signals. This kind of approach is called frequency division multiplexes, or FDM. So frequency division multiplex. And this is a very familiar concept to all of us, right? Because what we do when we're broadcasting, we actually use frequency division multiplexing. If you think about you listening to the radio, and they repeat all the time some numbers. They say 98.5 or 104.1 or whatever they say. Whatever the number that they're repeating is actually this number, this frequency at which, so when they say WFIT 98.5 megahertz, what that means is that the baseband signal of WFIT, which is music and talk and all of these signals that are in a range from 0 to 15 kilohertz, is actually translated to the frequency of the carrier that is 89.5 megahertz. And there's 150, actually 200 kilohertz nominally around this carrier frequency that we use for transmission of this signal. And then next one over would be 89.7 would be the next 89.9, 90.1 and so on. So this is how all of our radio broadcast is stacked. The same thing happens with the broadcast television. Usually the frequencies are not a little bit higher. With broadcast FM radio at around 100 megahertz, with broadcast TV around, let's say, 500-600 megahertz. So that's where the TV stations are. And then they don't use AM, neither one of them. But if some of you are still familiar with AM broadcast is using single sideband AM, and it's nominally 5 kilohertz, so it's lower quality. Actually, I'm not sure, it's probably using, no, what am I talking about? It's using double sideband with a large carrier, but the bandwidth at the baseband is 5 kilohertz, and then it's translated to a few hundred kilohertz. The AM broadcast is, I don't know exactly, but 5, 6 to 11, 1200 kilohertz. So sub 1 megahertz of the carrier frequency. The baseband on AM broadcast is 0 to 5 kilohertz, and we all know that because you don't really use AM to listen to music, right? It's usually talk shows and stuff that where you transmit voice, and the music sounds really, really muffled because you don't have any of the high frequencies that you have on an FM broadcast. So that's the fundamental way of how we use modulation to multiplex the signals in the frequency domain. And as I said, the main purpose here is to use the same transmission medium to send multiple signals. And then when you demodulate through the process of filtering, you're actually going to eliminate all the other ones but the one that you care about. And what you're doing on old dials is exactly that. You're actually selecting the station. You're moving the filter to the station that you desire. And if you happen to have an old radio that's analog, you know that if I put the filter here, I might be actually hearing 2 stations at the same time, especially on AM, right? So, but now everything is digital. What you do is you just say, I want to listen to this particular number or this particular station, and then it digitally tunes to the carrier frequency and demodulate whatever station it finds there. Okay, so that's a story of the single sideband. In summary, it's a very efficient modulation. It does not use more spectrum than what it's absolutely needed. If you cannot eliminate more than a sideband, because then you're eliminating information. But adding anything beyond a single sideband is adding redundancy to your transmission. So it's as efficient as it can be, but it's relatively complicated. You have to do a lot of processing at the baseband. You have to make sure you have a Hilbert transformer at the baseband. And you will see later in this course, it is very sensitive to the noise. Among all of these modulation schemes that you're going to cover, it turns out that single sideband is the most sensitive to the noise. So what that means, your signal-to-noise ratio needs to be very high if you try to demodulate it. And there are all sorts of issues associated with how complex it is and all the linearities that you need to maintain along the way to make it successful. Nevertheless, there are a lot of cases where the bandwidth or the available spectrum is of the highest importance, and anything you do on the signal processing in those cases is justified by how expensive the spectrum is. Okay, there's a homework associated with this. As you know, I assigned both exercises and in the homework. Exercises are from the Shams manual, so you can take the problems 3.9, 3.10, 3.13, 3.14, and 3.15. And then from your textbook, good problems to look in are 3.9, 3.13, and 3.16. Those problems exercise the material that is covered in this class. Okay, that's it for now.